So thank you very much. So the plan of, so everything I will talk about is joint work with a number of people in different works. So first, Leonor Godinho, there is a paper with her that is the beginning of everything, and then with Leonor, some other people joined the crowd, which is Carlos Florentino and Indranil Biswas. Sorry for the non-alphabetical order. Actually, it's anti-alphabetical, so it's fine. And we completed the work. So the main result that I want to present is the existence of an isomorphism between two spaces that I will call X alpha and H beta. And these spaces, they appear in different frameworks. So the X alpha, it's what I will call the Hyperpolygon space, and has been much studied in symplectic geometry with symplectic techniques by Konno and Harada Proudfoot. There are a number of works. And H beta will be the moduli space of some parabolic Higgs bundles with a number of assumptions that I will, parabolic Higgs bundles on CP1. Okay, and there are a number of assumptions that I will specify later. For the moment, I will just leave some dots. So the first aim of the talk is to give the existence of this diffeomorphism. In fact, it's a symplectomorphism, as we prove later. So it will take a while first to introduce both families of hyperkähler spaces, and then to establish explicitly the isomorphism. So I will start by introducing two relevant submanifolds of these spaces that are respectively what's called the polygon space and the moduli space. So this is a moduli space of parabolic bundles on P1 with the same assumption as above. Okay? So the root of the talk will be, I will start from this one, and then I will move up to the hyperpolygon space, then I will start from this space, I will move up to the moduli space of parabolic Higgs, and then I will establish the isomorphism. And then as a application, I will talk of fixed points for some relevant involution that relates this to branes and similar assumptions. Okay. So as promised, the first character of the talk is the polygon space. So I'm not sure how much I should assume. Please feel free to interrupt me for questions and things. So polygon spaces, I will introduce them as follows. Let's fix n positive numbers. And let's consider the product of n spheres of radius alpha I. So each of them is a symplectic manifold with a standard volume form. And on the product, we can consider just the symplectic form given by the pullbacks of the symplectic forms on each of the components. So this is a symplectic manifold on which we have the action of the group of rotations that acts diagonally on the product of spheres by rotations on each of the spheres. And this action is not difficult to see that it's Hamiltonian, which means that there is a map, the moment map, to the dual of the Lie algebra of SO3 that I will identify with R3, right? And this map is the following. It's not difficult to see. One take n vectors in this product, and so if it was just one sphere, it would be, the moment map would be just the inclusion, because we can think of it as a cojoint orbit. And as it is a product, we will have the sum of the VI. So the polygon space that I promised to introduce is the symplectic reduction with respect to this section. So the product of two spheres reduced by the SO3 action at the level 0. So if you're not very familiar with symplectic reduction, what this means is that you take the 0 level set for this map upstairs, and topologically you take the quotient of this manifold by the group SO3. And the relevant fact is that by Marsden-Weisstein reduction theorem, this inherits a symplectic structure as well. So this is what I call the polygon space. Okay. So why do I call it so? Right? So what does it mean for vectors v1, vn to belong to this level set? It just means that when we apply the vectors in R3, one after the other, the last one is coming back. v1, v2, etc. The last one closes. Okay? So this, you should think of it in R3. This is what I call a polygon in R3. Right? It's a piecewise linear thing. And we are considering the moduli space of all such closed configuration where we fix the length of the edges modulo rigid motions in R3. Good. So what is this space? So let's see a couple of examples. For example, let's do this. This is the space of polygons with length given 5, 1, 1, 1. Of course, there is no, exactly. There is no polygon in here, so this is the empty space, but good enough, we have better spaces to study. I just want to remark that this happens every time we have one edge that is much longer with respect to the other. This will make sense soon. And for example, if we consider the equilateral case, this is clearly non-empty because, for example, we have the class of the square sitting in there. But also we have a line configuration as follows. So we have, for example, two edges going to the right and the other two coming back on the same. So this lives in the 0 level set, but it's not a good configuration because the S1, the isotropy of this configuration is the rotations around the axis, with axis the axis where the polygon live. So this will give us a singularity in the quotient. Okay? So this justified the following definition. So alpha is called generic if and only if the following scalar quantity, sum of the alpha I for I in an index set minus the sum of the remaining one. This is never 0 for any choice of the index set 1 through n. Okay? And as I will use this inequality a lot, I call it epsilon S alpha. And M alpha is a smooth scalar manifold when alpha is generic. Okay. Are these lines set for the filming? Yeah, okay, so I leave them there. Very good.
Everything is safe. I think everybody uses all board.
Okay. So, good. This is what I wanted to say about polygons, at least the first introduction. So there is another way to describe polygons, which is via quiver varieties, which is, I mean, just a rephrasing, polygons as quiver. So let's consider the following quiver. We have n plus 1 vertices and arrows as follows. Right, all pointing to the inside. So to construct the Kähler variety associated to this quiver, I need to choose the dimensional vectors, so vector spaces for each of the vertices. And I choose Vi to be C and V0 to be C2. This is for I that goes from 1 through n. And then with this choice, the representation of the quiver I've drawn is just homomorphisms from C to C2, and we have n copies of it, right? One for each of the arrows. So homomorphisms between the vector spaces, it shows whenever there is an arrow connecting the corresponding vertices. So this is just another way of writing, let me go down, of writing the cotangent of writing C2n. Just with coordinates qi, where the qi are maps from C to C2. Good. Then the group, the Nakajima recipe to construct the quiver variety, say to consider the group of automorphism. Let's do like this. So this is U2 for the endomorphisms of C2, and U1n, it's a torus of diagonal matrices in UM, and I quotient out by the diagonal S1. Okay? So K acts on C2n by conjugation. And do I want to say the moment maps? Probably so. Yeah. So with moment map, this is a little bit. Well, let me drop it. So the polygon space M alpha can be described as the symplectic reduction by C2n of C2n by K at the 0 alpha level set. Okay? So the result in this language is I should credit it to Milson and Kapovic, even though they don't use the quiver language, but I think the idea is somewhat in there. Okay. So why is this true? How does the identification between the two spaces go? So so in fact, I mostly care about the generic case, but I think, if I'm not mistaken, that the result holds also for non-generic. It's really, I mean, the thing is you're just doing symplectic reduction in stages. So if you do the reduction first by the U1n component, you get a product of CP1s that I can write as spheres. And then if you do the reduction with respect to the residual SU2 mod S1 SO3 group, you get the description I gave before. So essentially, the description I gave before, it's a zoom in this part. And what I'm saying is that you can do just the quotient directly by the product group. Yeah. I started with this description not only because I liked it, it will play an important role right now. I mean, so what is the, why did I zoom in so much? Why do I care? What I wanted to say to describe is the following. It's what I call the polygon game, just because I like it very much. So what you do is the following. You take your favorite Lie group and consider some coadjoint orbits in the dual of its Lie algebra. Coadjoint orbits. And then, of course, each of the cojoint orbits is symplectic, and so it is the product of these orbits. And then you have the group G that you started with that acts diagonally on the product of the cojoint orbits by the cojoint action. And the moment map takes values in the dual of the Lie algebra of the group. Let's call it mu. And then you may wonder what is the space that you construct, let's call it MC, by taking the symplectic reduction with respect to this group action. Okay. So if you do it for SU2 or SO3, what you obtain is the polygon space that I just described. Right? But it is interesting to do it for other groups. Of course, describing the space gets immediately kind of more complicated. But we will see other polygon spaces appearing during this talk. Okay. Questions? So let me move on to the upstairs to the hyperpolygon space. So to move to the hyperpolygon space, my approach will be just to double the arrows in my quiver and construct the hyperkähler manifold that I obtained from the doubled quiver. So in terms of the representation, I wanted to do it there. Can I write here? Okay. So now the representation of my new quiver, let me call it Q tilde, is again homomorphisms whenever I have arrows. But now I have what I had before, so homomorphism from C to C2 and copies of them for the white arrows. And then I have homomorphisms from, sorry, with so much blackboard, homomorphism from C2 to C. Okay, so in here, this is just another way of writing the cotangent bundle to C to N, and we are considering coordinates. Sorry, let me do it like this. Fine. So we use coordinate PQ, where P are maps from C2 to C, so they are row vectors, and Q are maps from C to C2, so they are column vectors. Fine. So the group K acts on the cotangent to C to N in what's called the hyper-Hamiltonian fashion. So I think here I can. What happens is that the cotangent to C to N is a natural hyperkähler structure, right? With respect to this section is what's called hyper-Hamiltonian. And now I want to write the moment maps because I want to comment on that. So I will take some space. Okay, so what happens? Essentially, we have on the cotangent to C to N, we have three Kähler forms. And as usual, I will pair the last two to a complex, to a holomorphic one. So with this notation, the action is again by conjugation as before. And the real moment map is as follows. Mu R P Q is just, there are some scalars, but I write the relevant QI star minus PI star traceless part. The star is transpose conjugate. And the norm of the QI star minus PI star, whatever. And what will be relevant later are, in fact, the complex moment map condition, which are that the sum of the qi, pi traceless part and the product pi, qi. Okay, I will now comment on all of them, but so what happens is that the hyperpolygon space that I wanted to introduce at the beginning is what's called the hyperkähler reduction with respect to this section. By k at the level set, so I want 0, alpha, 0, 0. So what does it mean? From topologically, what we are doing, we are taking the 0 alpha level set with respect to the real moment map. We intersect it with the 0 level set for the complex moment map. And on this submanifold, we have an action of k, and we consider the quotient by k. So topologically, this is what you do. And then, again, it is pretty amazing that this inherits an hyperkähler structure. So it is an hyperkähler manifold. When? So this is smooth, it's hyperkähler, and it's smooth, again, when alpha is generic. It's not difficult to prove. So the genericity condition is, again, that one that I have over there. OK, good. So maybe you, at least I am very fond of the simple description that we have for polygons, even if they encode a very interesting geometric structure. So you may wonder, so, OK, fair enough, but what are hyperpolygons? And in fact, Bolch proved that, that these hyperpolygons are in fact, so let me, hyperpolygons are SL2C polygons. Okay, so essentially what you do is you play your polygon game starting with the group G being SL2C. And if you perform all the reduction, what you obtain are hyperpolygon spaces. So there is a relation between our SL2C and SU2 that gives us the polygon space in R3.
So you take endpoints in the C2, and you fix the length of the edges connecting these points, and you consider the space of such.
No, you take endpoints in the Lie algebra of the group that you are considering. So this, yes. So this is a good remark. So these are polygon spaces in G star. Okay, so they have, in here it was in R3 because we were doing SU2. But these are polygons in the Lie algebra of the group that you consider. So you take n points in C3, or if you prefer the description as the Lie algebra, the dual of the Lie algebra of SL3, and you are fixing the, in fact, if you think of them as matrices, what you're doing, you're fixing the spectral invariants, the eigenvalues. Or via this identification, you're fixing the length. Okay, so here, maybe I should have noticed before. Here I started fixing the length, etc. Where is this fixing the length appearing in here? It's in the choice of the quadjont orbit that you make that is characterized by the spectral invariants, right? So for SU2, we only have one, and they call it the radius of the sphere, but that's how it goes generally. Okay.
Do you assume these matrices are semi-simple?
Sorry?
You have n matrices, 2 by 2. Do you assume they're semi-simple? What do you do with Jordan cells? They're not characterized by spectral invariants.
Yes. Do they give rise to generic points. No, I don't assume they are semi-simple. No, I mean, I'm.
They're not generic because the eigenvalues are
Yeah.
the same for
Yeah.
non-semi-simple matrices. So you just throw away all matrices with equal eigenvalues?
No, I don't. So maybe so what you want to do is really fixing the coadjoint orbit. That is the point. So yes, you're right. I was oversimplifying now. It's really the choice of the coadjoint orbit. Good. So I think this is all I wanted to say for the right side of the original diagram, and I would leave polygons and hyperpolygons aside for a while and introduce parabolic Higgs bundles and then establish the correspondence. Okay. So parabolic bundles. I mean, of course, the setup can be much broader, but I will already make the restriction that I need. So I only take holomorphic bundles on CP1 and consider in CP1 n distinguished mark point. Okay, I will call D the divisor associated to this point. And so a parabolic structure is on E. Is the choice of a flag in each of the fiber of the mark points and of weights. So let me call this beta 1 xi smaller or equal than beta 2 xi and actually equal not. Okay. So what's and you do this for every x in the collection of mark points. Okay, so it's a choice of a complete flag and parabolic weights in each of the fiber of the mark points.
You mentioned rank of bundles.
Is 2, yes, sorry. I mean, of course, you can do the theory for much bigger case, and I will comment later. So I take your question to make, I mean, it is 2 because I want to establish the correspondence with SU2 and SL2 polygon spaces. But of course, the role of the rank should be thought as this number here. Good. So there is a notion of stability that is the following. So you define the parabolic degree of the bundle E to be the degree of the bundle plus the sum of all the weights, beta 1 xi plus beta 2 xi. Okay, and then the slope, the parabolic slope of E is just the ratio between the parabolic degree and the rank, which in our case will be always 2. Okay, and then E is said to be stable if and only if the slope of any subbundle is strictly smaller than the slope of E, of any parabolic subbundle. And it is semi-stable if the equality can hold. Okay. So with this notion of stability, people have studied the associated moduli spaces of, so the one I will consider are moduli spaces of stable parabolic bundles on P1, fixing the topological invariance, so with rank 2, as we said. And I want them to be holomorphically trivial. Okay, this is a pretty strong assumption, but it's needed for the. And this space is the one I will call M beta. Very good. So I think this is all. Actually, so when is this moduli space a smooth manifold? So M beta is smooth if and only if there are no strictly semi-stable lines of bundle. So stability is equivalent to semi-stability. Okay. So in our case, with just rank E and the degree being 0, you can sit down and do the computation. So what does it mean? I like to draw, so let me draw. What does it mean to have a line subbundle? So L in E is a line subbundle. What does it mean to be parabolic? Well, essentially, on the fiber, there is nothing we can do. That is C. It has somewhat trivially a parabolic structure. But you still need to choose a weight, beta L xi, right? So the way to assign the weight is the following. For every of the mark points, you have a copy of C2, which is the fiber over there, together with a flag, so with the choice of a one-dimensional subspace. And weights, so the one-dimensional subspace has weight beta, what was it, beta 2? And the two-dimensional has weight beta 1. So if your line subbundle Lx intersect the one-dimensional subspace only at the origin, then it inherits the weight beta 1. If it coincides with the one-dimensional subspace in the flag, then it inherits weight beta 2. So this is beta 1 xi if Lxi intersected with EXI2 is just the origin, and it's beta 2, sorry, xi otherwise. Right? So you sit down, you do your computations, and you figure out that M beta is smooth if and only if this quantity, sum of beta 2 xi minus beta 1 xi for I in S, minus the sum of the same quantity for I in the complement. Okay, so if this quantity is never 0 for any choice of index subset that you can make in 1 through n, then your moduli space is smooth. And you have already seen this equation. Actually, I've just erased it, just with a different name here. So this is what started to ring a bell for us that this difference between the parabolic weights seems to play the role of the length we chose, right? But before, and it does. Yeah. So before going along with the isomorphism, let me move to the hyper word here as well. So introduce a Higgs field on these parabolic bundles. So let E be a parabolic bundle as in here. Higgs field phi is an element of the H0 P1 with value in the sheaf of strongly parabolic endomorphisms of E twisted by K is the canonical bundle of P1 and D is the divisor associated to the, okay, this is my notation. So if you are unhappy about the definition, you are like me. I was very unhappy when I saw it before. I thought, and then, so, okay, I haven't defined a number of things here, so maybe I should say what a strongly parabolic endomorphism is. So this is an endomorphism of the bundle such that f of exij is included in the smaller one. Check. Okay, fine. So what is it? The way I think of it, and it will be handy for the construction of the isomorphism, for me the Higgs field phi is a 2x2 matrix of 1 forms that are meromorphic exactly at the chosen point, and that is nilpotent with respect to the flag. Okay. Higgs field. Fine, then, I mean, E phi is a parabolic. So a parabolic Higgs bundles is just the pair of a parabolic. By D, exactly. Maybe I can make it more explicit. Yeah. Okay. So this is really not, in a way, I mean, we landed in this wonder world of Higgs field as a venture. But I really like, well, I will convince you later, I really like the existence of isomorphism between, because if I think of them in terms of polygons, I think it gets much more clear. Anyway, so the notion of stability extends naturally, so essentially you just require that the same condition holds for parabolic Higgs subbundles, so parabolic subbundles that are preserved by the Higgs field. Stability extends. And then people consider the parabolic, the moduli space of such bundles. So I'll do it as follows. I will already define the moduli space that I am interested in that comes with a number of assumptions. So this is the moduli space of parabolic Higgs bundles on P1 with, of course, rank 2, holomorphically trivial. What do I want? I want trace-free Higgs field and fixed determinant. Fixed determinant bundle, and I haven't forgotten anything. Very good. So I am aware that I haven't said a word about this last two assumption. And if you allow me, I mean, they are a little bit technical, but nothing very, I mean, it's very usual in the study of this moduli space to require these two conditions, and in my mind, they come as some sort of level set cutting. So I will leave that part a little bit under the reg. So, but an important thing to say is that Kono gave a description of these spaces as so constructed an hyperkähler structure on these spaces by gauge theory, so as an infinite dimensional quotient. Okay. So I think I am now in shape to state finally the theorem. Which is the following. So this was proved with Leonore and myself quite some time ago. The result is the following. So you fix, as we said, distinguished n-mark points in P1 and parabolic weights beta such that that is generic. So there are no strictly semi-stable subbundles. Then H beta is isomorphic to X alpha, where alpha I is equal to beta 2 xi minus beta 1 xi. Okay, so this was is the result. And how do we prove this isomorphism? So we really construct it explicitly. So I will present here the construction from hyperpolygons to parabolic Higgs bundles. So if I take an hyperpolygon, which is a class PQ, remember, I need to construct, to associate to it, a parabolic Higgs bundle E phi. So the parabolic bundle, there is nothing to construct because it's holomorphically trivial. So this is CP1 times C2. Good. Oh, no, there's no choice. Then I need to give a parabolic structure. So what is a parabolic structure? A parabolic structure is for each of the flag the choice of, let me do, I still have it here, a full flag. So the fiber is C2, and I need to choose a copy of C inside C2. We have a prescribed way of choosing a copy of C inside C2, the map Q. So I say that this C is the space generated by Qi, or if you prefer, this inclusion is Qi. Remember from the quiver description, we had that here we had coordinates PQ. Q were maps from C to C2, and P were maps from C2 to C. Okay, so this gives us the flag. The weights are assigned at the beginning. And how about the Higgs field? So the Higgs field, here it comes. So I told you that I think of it as a 2x2 matrix of meromorphic one forms. So I said that I want the residue of my Higgs field to be Qi, Pi, traceless part. So this is a 2x2 matrix, right? It's a product. And if you remember the moment map conditions that were written exactly here, I shouldn't have erased it right now. This appears, so there was a moment map condition from the complex moment map that was exactly that the sum of the Qi, Pi, traceless part was 0. This was one of the moment map conditions. So what happens is that I have n residues summing up to 0. And for the residue theorem, there exists a unique phi satisfying this condition. Here we use that we work on P1. Okay. And the vice versa, I haven't prepared for this presentation because it's a little bit, you start choosing A, B, C, D, and then blah, blah, blah. But it is extremely explicit. So what you do, you take a generator of your flag, you look at the residue of your Higgs field at the mark points, and from the entries of the residues, you construct your P and Q. So it's a very explicit construction. Okay. So this worked very well for us because we were in fact, so we started all this big trip. So both me and Leonore, we are symplectic geometers, and we were studying these hyperpolygon spaces, wondering word crossing problems with respect to alpha. So it took us a long tour to the Moduli space of parabolic Higgs bundles to figure out that the problem of word crossing, for example, for these spaces had been completely solved by Thaddeus. And then all we did was to translate it back using our map. So it really, it does work as a dictionary. But anyway, in this talk, as an application of this result, I decided to start to talk of fixed points for some involutions. So let me remark that in here, I do it in, I don't know, I think yellow, maybe you see well. So this isomorphism is in fact S1 equivariant with respect to the S1 action that multiplies the P coordinate, or let me do lambda, and multiplies the Higgs field. Okay. So in particular, if you are interested, so fixed point for involution. Involutions. So what happens is, if, for example, we were interested in studying what are the fixed points for the involution that change sign to P. And in terms of Higgs fields, parabolic Higgs bundles, this means that you change sign to the Higgs field. Right? So what are the fixed points for these two involution? Again, you sit down. So this is joined with Leonor Godinho. Let me be. So Indranil Biswas, Carlos Florentino, Leonor Godinho, and myself. So the fixed points components, or the fixed point set for this involution is the following. So if you want to use the language of hyperpolygon spaces, what you obtain, of course, polygons are fixed, because if the P coordinate is 0, this is clearly fixed. So polygon spaces are a fixed component. But then there are some other components that are indexed by, we call them ZS, where S is an index set of cardinality at least 2 that is short. So what does it mean to be short? It means that epsilon S alpha is negative. Remember, this is the difference. This is the difference between the sum of the alpha I for I in S minus the sum of the alpha I for I in S complement. So if you want to keep it in mind in terms of polygons, this just means that you have this polygon belongs to your space, right? Where these are the VI for I in S. As it is short, you can put them on a line, and the others still close. Okay, so when S is short, such configurations are allowed, just to give a geometric ending. So fine, we have this component, and the components that S, they are defined as the collection of hyperpolygons such that, what are the conditions? S and S complement are both straight, so let me, instead of Qi is a multiple of lambda of Qj for every I and j in S, and also the other Q's are multiple for L and K in S complement. And moreover, the Pj are 0 for every j in S complement. So if you are unhappy, it's a very explicit description, but you may be a little bit unhappy because there is not. One loses a lot of the geometric intuition. So what does it mean in terms of parabolic Higgs bundles? So if we apply our isomorphism and checked what are the fixed points for the associated involution, we obtain, let's say, similarly or consequently, in terms of parabolic Higgs bundles, we have, of course, parabolic bundles with Higgs field identically zeros. They are fixed by this evolution. And also we have some other components that the paper, we call them curly S. I will try to make it very curly ZS. Again, this is exactly the same set, just translated. And what are our characterized bundles in ZS? Where Phi in ZS is such that, so what happens is that the bundle splits as the direct sum of two line bundles, and the residue is either upper or lower diagonal. So this is for I in S, and the residue of Phi at X. J is lower triangular for this. So I hope you are very unhappy at this point, because this result is very explicit, but still, what does it mean? And I hope you are unhappy because there is a surprise coming. So this component ZS that are described near, if you stare at them for long enough, you realize that they are also polygon space for another group. Which group? The other real form of SL2C. So one of the real forms is SU2. The other is SL2R, or the pseudo-unitary group SU11. Right? So let's do polygons. So I have already given out the surprise, so these are polygons for SL2R. What is the Lie algebra of SL2R? It's the Minkowski 3 space. Minkowski 3 space. So let me recall, because maybe you as me before starting this didn't remember. So I will identify it with R21. And what it means is, so if I have, what do I do? I do two vectors probably. So essentially, let's say we call x, y, t the coordinates. The product of u with itself comes with a negative sign for the squares of the first two coordinates and the positive sign for the square of the last one. And so with this inner product, we have that the vectors u are classified according to their product. So they are called space-like if the product with themselves is positive, I believe, if I'm not mistaken. Yeah, negative, I am mistaken. And then they are light-like if it is 0, and time-like if this is positive. Okay, so what happens is that here we have the light cone of light-like vectors. And then we have, in here, we have future vectors, past vectors in the lower part, so with negative t vectors. And here around, we have space-like vectors. Okay, so this is a way of identifying our dual of the Lie algebra with this space. Okay, so let's see how one constructs this identification. So what are the coadjoint orbits for the pseudo-unitary group? They are the pseudospheres, as they should be. So if you consider SR plus or minus to be the collection of points x, y, t in R21, such that minus x squared minus y squared plus t squared is equal to r squared. Okay. This is a two-sheet hyperboloid. And depending if we choose t to be positive or negative, we have what's called the future, if t is positive, or past, if t is negative, pseudosphere. Future, past, pseudosphere. Okay, maybe I can try to draw, not promising a great result, but this is our future pseudosphere, and this is the past pseudosphere. Okay? So, again, not difficult to check that SR plus minus are SU11, or if you prefer, you choose the notation you like best. So to our coadjoint orbits. And so you can play the polygon game. You can take a product of them. So let's take a product of some, let's say, alpha I future pseudosphere for I in an index set S, and a bunch of past pseudosphere for I in S complement. This is, again, a product of coadjoint orbits. It has the action of our group SU11 that acts diagonally by the coadjoint action, and this action is Hamiltonian with moment map in R21 that is just given by taking the vectors U1, UN, and it takes them to their sum as vectors in the Minkowski 3 space. So when we construct, now I call it MS alpha, the symplectic reduction with respect to this product of past and future pseudospheres by the action of SU11, we obtain, again, a polygon space. What is a point in there? Well, it's a collection of cardinality of S future vectors, so they go up like there. I make them in blue. And then there are cardinality of S complement past vectors, such that when you put them together, they closes. Modulo rigid motions. Okay. So, yeah, well, maybe you believe that the relation exists. So these are in particular non-compact submanifolds. And again, now we established very explicitly again the isomorphism between this component ZS and our polygons in the Minkowski series space. Maybe the isomorphism is less satisfying. So the theorem we have with Indranil, Carlos, and Leonor is that the components ZS are diffeomorphic to the polygon space in the Minkowski 3 space. Again, you can, so the way you do, you take PQ in here, and then this is really, so you associate to it the vectors UI. So you associate U1, UN, where UI, I can write it for you, but it's very PI star, PI minus QI, QI star, traceless part, plus a half, whatever. So how do we come to this isomorphism? It's not that we crazily multiply 2 by 2 matrices randomly. So you look at the moment map condition and you search. So you search on how you can choose the vectors so to obtain that, for example, they will be indeed light-like and that they will have the appropriate length. So this UI, they are vectors of length alpha I, where length is measured with respect to this inner product. So in a way, what's the English word? So this isomorphism is hidden in the moment map somehow. You need to discover it. So okay, this is all for what we have done. There is still some to come, because of course there is a missing character in this picture, because we only have obtained time-like vectors and only considered one type of cojoint orbit for SU11, which is the two sheets hyperboloid. Okay? But there is another type of cojoint orbit of this group that is the one sheet hyperboloid, corresponding to the choice of space-like vectors. So where are they? Why they don't come into the pictures? They come into the picture, and we are writing it now. So if you consider the involution that takes a parabolic Higgs bundles Phi to the dual of the bundle and the transpose, or we can, of the Higgs field, and you study the fixed point set for this involution, and you use the moment map, you can identify them with polygon spaces where you consider the space-like. So this is yet to come. And I want to finish, I don't know I'm doing time-like, but I want to finish with a final remark. I've realized while I was talking, I'm sorry, I apologize, I haven't said anything about the references. I mean, of course, there is a lot of work on all these things. So in particular, at this point, I want to mention there is a work of Steve Ryan and Jonathan Fisher. They consider it an analogous case where, so what they do is they take the star-shaped quiver, as we did, and instead of choosing vectors, 1, 2, n, so they choose dimension vectors. For V0, they do C3. And for the VI, they do C. And then they run the same machinery. This is equivalent to consider SU3 conjoint orbits, where, so you take the conjoint orbit that is a degenerate flag, so it's missing the two-dimensional space in between. And they work out so they do, they study this, sorry, I haven't put the arrows. They studied this situation and showed that it is equivalent to parabolic Higgs bundles of rank 3 on P1, and with the same assumption as we have. So this is Ryan and Fisher. And there is also work that I'm not sure at which state it is, from Thomas Hausel, Michael Wong, and maybe somebody that I am forgetting now, about what they call a comet-shaped quiver. So what you do, you consider a quiver like this, right? So here, say you choose n, and then you can choose whatever weight you want on these. And this corresponds to considering, so if you run the Nakajima quiver variety thing, so this corresponds to considering a product of SUN coadjoint orbits, where essentially the length of the leg of your comet tells you the level of which coadjoint orbit you took, the level of degeneracy. And they relate this to parabolic Higgs bundles to of rank n. Okay, so this is what I wanted to say.